Welcome once again to the next segment of our class. I'm going to treat example 2.3, where we are given a three-phase, three-wire star-connected load connected to a balanced three-phase 380/50 Hz delta connected generator. The impedance of the load are given. They said we should take VBC as reference with positive phase sequence. VBC as reference. If VBC is the reference, we are going to assume VBC is at angle 0 because they didn't specify any other angle. And if it's not specified, we could just take as VBC as angle 0, right? Then the next thing is you want to determine the direction of rotation sequence, which is, we said, is positive phase sequence. So if it is positive phase sequence from here, you are going to have VAB at this angle and VCA at that point. Then from there, you can make some determination for other phase voltages, like because it is positive, our line will lead the phase. So this will be VBN, whereas this will be what? VCN, and this will be what? This will be VAN, and that is how it goes. This will be at minus 30 degrees, right? Since this one is minus 120, this will be at angle what? Minus 150 degrees. So that is how our phasor diagram goes. Now, looking at the circuit as it is, they said is such that we have a star connected load, where a star connected load that suddenly the voltage, the impedance at phase A suddenly goes to infinity. That means it is open circuited. So, and they want you to determine the voltage at that point. The voltage at that phase, at the instance of the open circuit. Calculate the voltage drop in phase A should the impedance in this phase suddenly goes to infinity. So you want to determine the voltage in that that voltage drop in that position. So this is A, this is C, this is B. Now this is Z, B, this is Z, C. Right. What you do is, when you take a particular point here, you can take this particular line. You want to use this as a closed circuit, and use Kirchhoff's law to be able to determine the voltage drop here. Then once you determine, the idea is you will determine if you can, the voltage across here is VCA, right? So if that is VCA and this is VA and this is what? This point is taken as N, this is VCN. If you look at it very well, taking this place as a closed circuit, VCA, VCN, VA, from what I proved to you last time, VCA will be equal to VCN minus VAN. So since we want to find VAN, which is this, all you need to do is, once you determine VCA and VCN, you can get the voltage drop at that point. So our work is to be able to determine this, then we'll get this. So to determine this, we assume that there is a current flowing from here, which is IC. And that IC, because here we are saying this is VCB, which is the higher potential. Current is flowing through this way. It will not go through here because this is an open circuit. So current is a high resistive part. So current will go through the least resistive part. So it comes through back to B. So with that, you can say the VCB, using Kirchhoff voltage law, you are saying voltage VCB, which is like the EMF driving the total voltage drop here, will be equal to the voltage drop here plus voltage drop here, which is what? VCN plus VBN, which is this. That will give you your VCB. So VCN plus VBN is IC is taken as ICB because it's the current flowing from C to B. That means it's a ICB times ZC will give you the voltage drop at this point, VCN, plus this ICB times ZB will give you the voltage drop at this point. So you can factorize. We have ZC plus ZB out, right? Then that is going to give you VCB. So all you need to do now is to determine what you have your ZC. Our ZC is given as what? Our ZC is given as 22.4 plus J 16.4 plus ZB, which is 32.6 plus J 12.6, right, times ICB is equal to what is our VCB? Our VCB, you can look out for it from the phasor diagram. If this is VBC, as we have it, right, our VCB will be opposite, which will be VCB, which will be at angle 180 degrees. So that means VCB is at angle 180 degrees. And what is the magnitude of VCB? What is the voltage given to us? The voltage given to us, which is the line voltage, is given as 380 volts. So this is 380 at angle 180 degrees. So invariably you find your ICB to be equal to what? To be equal to 6.112 at angle 152.2 degrees amps. That is your ICB. And your ICB is also, which is your current flowing from here to here, is also the same thing as your IC. Right, your ICB is going to IC. Now that means we have determined the current flowing from here to here. So based on that now, we can, once we have determined that IC, we can now determine the voltage drop here. The voltage drop here will be the IC times ZC. So VCN, the voltage drop here, VCN will be equal to IC times ZC. And what is our IC? Our IC is ICB, which is given as 6.112 at angle 152.2 degrees times your ZC. And what is our ZC? Our ZC is given as 32.6, that is times 32.6 plus J 12.6, J 12.6. So that is our VCN. So our VCN, when it is calculated out, is given as 213.616 at angle 173.33 degrees volts. That is our VCN. That is the voltage drop here. And once you have determined the voltage drop at that point, and you are what you are looking for is VAN, and you already know this voltage here, and you can determine, and from here you said your VCA is equal to VCN plus VAN, right? So what is your VCA? Your VCA is given as what? Your VCA from the from your phasor diagram is given as at angle minus 120 degrees, right? So that means you have your VCA as 380 at angle minus 120 degrees is equal to VCN, which is what we have just calculated, 213.616 at angle 173.33 degrees, right, plus VAN. So your VAN, you can now find your VAN out to be what? 354.589 at angle 93.58 degrees volts. So that is your VAN. That's the voltage drop at the point, at the instance when this phase impedance got disconnected, when it was open circuited, when it's just cut off, where that point leads to infinity. Thank you.